I'm pleased to introduce Dr. Agustinus Kristiadi. He works with Alain Asper-Gusick and Pascal Poupart. Got his PhD from the University of Tübingen in Germany, where he was advised by Phil Hennig and Matthias Hein. I will let you take it from there. Thank you very much.
15 minutes is on. All right. Today I'm going to talk about how can we use probabilistic inference for doing LLM decoding. Okay. So what do I mean by decoding? Well, decoding is basically just autoregressive text generation. So let's say you have an LLM F data here. It will take your context X0, and then all the previous tokens that you have generated, X1 to Xt, and then it will give you a categorical distribution, right? P of X, D plus 1 given those things, right? And this is basically probably an element of the simplex of this one here. And this is a very high dimensional simplex because it has many choices, right? And phi here is the size of your vocabulary, essentially. So this is the image here. So when you think about it, this autoregressive process is actually a process of building a source tree. What do I mean by that is that, let's say you have the root node is your context, okay? And then you'll be presented many options that you can choose. And for each of these option, you will have another many options, right? And so on and so forth. So it's building a tree, essentially, until the terminal nodes in either like at the maximum depth or you come to EOS node, essentially. So what would be the generated text in this context? Well, that would be a path from the root of the tree until the one of the leaf of the tree, right? So this tree is very huge, okay? Because the vocabulary is really huge. And how can we pick which one should we pick? Which paths should we pick? Which paths that correspond to our general text should be picked? That's the question. So a common objective would be that we want to maximize the likelihood of the path. So basically, at each path, you get the probability from the LLM, right? You just add all the log probabilities, essentially. And this is an optimization on tree problem, right? It's kind of non-standard compared to standard optimization problem. So this is combinatorially hard, and so that people use much more of a heuristic approach in this case, right? So for example, beam search. In beam search, this is basically the standard in machine translation, and at time step t. Oh, sorry.
Yeah, just a quick question, clarification. I mean, I guess you could just choose the most likely next thing, but the key is one that ends with EOS.
Yeah,
right. So
the one that's
sample conditioned on landing on EOS for a particular length as well, right? You want to generate a length, some particular length, right?
Exactly. Yeah. So it's something that's maximizes at this particular length, not just at each step, essentially, right? So it's harder because you have a sequence that has a length t in this case, right? So one of the approaches beam search was very easy. So basically, you have a beam. A beam is a set of partial sequences that we currently have. For example, here's beams of size 2. And at each time step, we basically just expand these beams. What do I mean by expanding is that just take your vocabularies, right? All the values in the vocabulary, and then you concatenate those possible values to all of your beams. And then you ask the LLMs, well, please score all of these generated sequences, and you just prune into two, in this case, 2 beams or P beams in general, right? So that's beam search, and then we just repeat. And this is problematic because we want to find the most likely path, not just the most likely token at each time steps, right? So it's greedy, and greedy is not optimal in this case, right? In particular, you cannot backtrack because let's say can you see your card? Okay. So let's say you are at this state of beam search, then you will not be able to pick this particular node anymore. So you cannot backtrack. So yeah, it's not optimal. And then if I want to do backtracking, what do? You can do Monte Carlo tree search. All right, Monte Carlo tree search is super generic. So you can use it for any kind of trees to do planning, essentially. For example, you might know it for chess playing trees, game trees, and then Go, for example, right? But you can also apply it to LLM search tree. So Monte Carlo trees has 4 steps. The first one is selection, and this is the different compared to beam search. At time step t during the decoding process, you basically have to start from the root, and then you use some kind of statistics based on samples, essentially samples of simulation, to pick which node should be expanded next. So let's say you come to this node. Then you do expansion. This is the second step. Yeah, we basically just attach all possible values of this particular node, and we pick one, and then to roll out. This is the simulation bit, right? You basically just continue down the tree until termination. For example, EOS token, or until you comes to the sequence length of t. And then, of course, once you arrive at the end, you know what is the likelihood value for this sequence, right? For the full sequence. And then you use that value to update all of the statistics that I mentioned before. And therefore, at the next iteration, the selection step would be would based on the updated statistics. So you can maybe pick this one here. So you can backtrack. And this backtracking is basically because of that the fact that you start at the root and then use some kind of selection policy. Yeah, can backtrack, but it's somewhat inefficient. 2 things, right? The first one is that Monte Carlo tree search is basically Monte Carlo integration. So it's the error goes down very, very slowly. And the second one is that you have to do rollouts. And doing rollouts is basically at each, if you go to this node, you basically have to ask the LLM once, and then go down again, ask again LLM, and so on and so forth. And you have to do it a lot of times for each decoding process. For example, for each context, you have to do a lot of simulation before you can get a good generated text, essentially. So that's bad. So here's our proposal. So we use probabilistic inference instead of just samples, stochastic samples. And also we also combine it with some kind of the nice thing about beam search, which is efficiency. So what is probabilistic inference? Well, it's basically that you have an unknown, and then you basically put a belief about this unknown, and then you have observation, and then you can combine them together, then you get posterior belief, right? And this posterior belief, you can use this belief to guide your decision-making process. So that's the idea. So what would the unknown here? Well, the unknown would be the likelihood at its path, right? At the termination, we don't know it. And then what would be the observation? Well, the observation would be the likelihood value that we have encountered in the currently expanded tree, the bold one here. And then we combine them together, and then we get the posterior, and then we use this posterior to make decision on which node should we expand next, and when should we terminate the decoding process. That's the idea. So the detail is this one here. Oh yeah, the method called ALTS. So uncertainty guided likelihood tree search. It's not on archive yet. Should be this week. So looking forward. So we basically focus at this current point for likelihood. So maximizing likelihood. Of course, there are a lot of other metrics like general rewards on LLM search tree that can be done, but this particular focus is on likelihood. So yeah, 4 steps, actually 3, because the very first step here, step 0, is actually just pre-computing the prior. So what we want here is to have a prior belief about the maximum likelihood, right? But that's kind of hard. How do you pick a prior for the maximum, right? So what we do here is use a simple prior. For example, the Dirichlet prior on the LLM softmax output. Remember that is a categorical distribution, right? And then we basically just compute the implied prior for the maximums. Okay, so we basically start from the bottom and then just go up recursively, just take the maximum of the samples. So it's a sample-based approach because the probability distribution for the maximum values would be intractable. Okay, but the nice thing about this step here is that you can only just do it once for each LLM. So basically you can do it once and then you can share it on Hugging Face or whatever, email it to your friend or something, right? And then your friend will not see this step at all. they will immediately see the selection process. So in the selection process, this is basically the same thing as the Monte Carlo research selection process, although we don't use the sample statistics like the empirical statistics in Monte Carlo research. In here, what we are using is the posterior belief that we have obtained. And actually, you cannot obtain the posterior because it's intractable, but actually you can make some assumption, and then the posterior samples would be available readily. It's easy to sample, but you don't know the exact posterior. And so we use all the samples to compute some utility function on which node should be expanding. All right, expansion. So basically just ask LLM, but now we just pick the top K children of such node. And then we basically observe their log likelihood, right? And then we use this log likelihood as new observations, and then we update posterior samples upward, just like a backup process in the Monte Carlo research. And notice that we don't have rollouts here, right? So it's much more efficient compared to Monte Carlo research, although you can actually extend it with the n-step look ahead, for example. And then we can repeat this until we are unlikely to obtain better log likelihood. So there are two things here where the posterior samples are used for decision making. The first one is selection, of course, right? And then the second one to terminate the algorithm here. So we can actually estimate the probability that the next value that we encounter if we go down this path of this tree will be larger than the current maximum of the likelihood that we have encountered so far. So we can estimate that. It's actually this one here. And then if the probability is very low, then we can basically just terminate, right? And what's the good thing about it here is that we have a selection process, just like Monte Carlo research. In particular, we can do backtracking, right? Because we always start from the root and then we do the selection. So we can do backtracking. And we also have a restriction that we impose here, which is we restrict to B beams per level in the sense that we cannot expand B number of nodes at each level. So it's similar like beam search. So yeah, it's a combination of both, but with additional flavor on top of it, which is probabilistic inference. And if you just care about NLP stuff, here's GitHub repo library. And if you compare it with beam search from Hugging Face, it's basically the same interface, right? Results. So we have multiple LLMs here, like Llama 2, 7 billion, Llama 3, 8 billion, KMI, and so on and so forth. And then we also have multiple data sets. The way to look into these plots is by noticing that the x-axis is the number of expanded nodes. So each node expansion means we call LLM once. So the lower it is, the better. So towards the left would be the better. And then the y-axis would be the log likelihood that we obtain. So the higher the better. So towards the left, towards up, that would be best, okay? So beam search would be in blue, and our method would be in green and orange. Those are just detailed like different priors that we use, basically. So yeah, as you can see there, our method is basically more efficient compared to beam search, but more likelihood. We can obtain more likelihood. So it's better than beam search while being efficient. Awesome. And then what about latency? What about overhead? As you can see here, the overhead is very small, and at each iteration of the tree search, we basically the cost is basically dominated by the forward pass of the LLM, right? And this will get bigger if you have larger LLMs. And yeah, almost 15 minutes, so future works. So yeah, so in NLP, it's well known that maximum likelihood doesn't imply that it's good in terms of perception of human evaluation, right? So I reckon that that's the problem of the miscalibration in the LLM itself, right? So if it were calibrated, then the likelihood will be perfectly correlated with what we expect, right? And then so yeah, so taking into account of miscalibration can be done by devising some prior here. And then for general maximization, I talked about likelihood here, but of course it can be done for different kind of values in the tree. And we can also do planning, as I mentioned before. And what happens if we also have answer and reward? For example, if you have a Bayesian reward model, for example, then having probabilistic formulation will be able, we will be able to incorporate those answer and rewards. And that's it. If you have a quick question, please do so now. But if you want to have a chat further, let's take it offline. Thanks a lot.
Right. Any questions out there?
So in the step 0 that you said is shareable, I didn't understand what exactly learning is. That the prior distribution over all the vocabulary over.
Yeah, no, it's a.
What's the output of step 0?
So, okay. So basically, what we want here is a prior over the unknown that we care about. What is the unknown? Well, the unknown would be what would be if I were to go down this tree, what would be the value, the likelihood value that I encounter, right? That's the unknown. And how can we see that? We don't know how to do it. So even imposing a prior directly in that region, it's not doable. So what we do here is to impose a simple prior on the softmax output of the LLM, like for example, to isolate, right? And then we compute the implied prior for the one that we actually care about by doing this process here. So we care about if I were in this part of the tree, and if I go down optimally, what would be the observed likelihood? So that's the idea. So that's why we basically start from the bottom here, and then go upward by taking the maximum over the samples. So that's the idea. And then okay. So the output of this procedure is actually a beta distribution, because it's a bit too much to gather samples and then share samples, because that would be a lot, right? So in terms of memory, so we basically just amortize the cost of this prior in terms of beta.
And also, you said that each LLM has to do this kind of implied prior once. So, but during this process, you have to go over the path, or
no, it's basically we have some kind of assumption there. Like for example, we have assumption in the independence between levels, for example, that makes it easy to compute, and so on. The reason why we need to do it once per LLM is that each LLM has different width, right? So in here, so the beta distribution will be over the weights, for example. So yeah. Any more questions?
Okay. Can we think of it as initializing the value function for Monte Carlo tree search using the greedy likelihood values? Like you're doing Monte Carlo tree search, but you start from some initial value which is based on greedy search.
I think I understand the question, although I couldn't hear it quite clearly. But I guess the question would be, can we actually commit a prior using some kind of some kind of empirical values, essentially, right? We actually have this kind of version of this prior. In here, I say e.g. to reach there, right? But you can do whatever you want, and then you can use any kind of prior that's on over the simplex, essentially, right? And in this case, as you can see here, we have alt Dirichlet and alt empirical. So the empirical prior is exactly what you just said. Yeah. Thank you.
Do you think it's possible to generalize this method to any graph-based search method?
For graph?
Yeah, for graph.
I think you need some kind of structure here. I know that you can do it for DAGs, Dirichlet, directed acidic graphs, but I'm not sure if you can do it for general graphs. So you need some kind of structure.
All right. Well,